Good morning. All right, I'm going to start off with the last set of reactions from chapter 10. And then today is mostly going to be kind of like a review, doing problems, and some more synthesis stuff today. We're not going to cover chapter 13 on the exam. We're just not going to get there. So on Monday, I'll go through the practice exams and kind of tell you which ones you can cross out and not worry about. So starting with some oxidations. So let's see. I'm going to kind of go back to this chart that we talked about a while ago. So we've been talking about this. We've really been doing reductions so far. So we know two different reagents that can do reductions. We're able to go from ketones to alcohols using NaBH4 and methanol. Or we can use LAH and water. We also know how to go from carboxylic acids or esters to alcohols using LAH. So as you might imagine, there are reactions that can go in the opposite direction. So today we're going to be focusing on going this way. It's kind of the same thing. There's two reagents. One of them lets you oxidize twice. One of them just lets you oxidize once. They're pretty straightforward. We're not really going to go into much mechanisms when it comes to these. So let's get started. All right, so there are two different oxidizers. That we are going to discuss. The first one is PCC, which is pyridinium calcium chromate. You really don't need to know the structure of this, but I'll write it down for you at once. So it's a complex. You have both pyridine with a positive charge on it, as well as CrO3Cl. This will do a single oxidation. So if we take a primary alcohol like this one, there are two hydrogens on this primary alcohol. It will do, PCC is a single oxidizer. So this is just going to push us to our next oxidation state, which would be an aldehyde here. If we use secondary alcohol, primary, we've only got one H. Yeah. When I throw in PCC, this will still do a single oxidation. To give me a ketone. Our other oxidizing reagent is going to be our stronger oxidizer. Definitely just draw on the table here. And this is going to be really just a long name. So Na2Cr2O7 in H2SO4 and water. These are considered to be pretty harsh conditions. We have 2 hydrogens, which means that we can oxidize it twice. This is a primary center here. So doing a double oxidation will get us originally to an aldehyde, but then this will continue to oxidize to a carboxylic acid. Secondary alcohols. So now we only have one H here. So when we throw in Na2Cr2O7, H2SO4, and water, this only has one hydrogen to deal with, so it can only do a single oxidation. So it's just like up top, this is still just going to give you a ketone. Okay, so that is everything that's going to be on the exam. I'm going to go through a bunch of problems today. We're going to do a bunch of synthesis problems. And then Monday, we'll go through practice exams. If they end up canceling in person, we'll just do them over Zoom. So I'm going to drop some problems for you guys. I'm going to give you guys about 5 minutes to go through them.
Blessing is closed on Sundays,
That sucks.
so we can't go to Blessing for Valentine's.
Oh, I see. I was like, what?
All right, you guys have till about 9:45, and then we'll go through these together. Next one, aldehyde. flip HD, right? Okay, so this first one here, we are doing oxidations. We are in chromic acid, which is a really strong oxidizer. We have both a primary and a secondary. So we can kind of break this into two parts. We have our secondary has 1 H on it. Our primary has 2 H's. So we will do a single oxidation for our here. OH that's on the ring. So this will get oxidized to a ketone. And then this primary one, yeah, people keep saying it's blurry, but I keep focusing it, and this is kind of the best it's getting to. Sorry, so primary one here can be doubly oxidized all the way up to the carboxylic acid. PCC, on the other hand, is just going to do a single oxidation. So we only have 1 hydrogen to oxidize here anyways. Let me try turning off HD and turning it back on, see if that helps at all. Maybe, I don't know. Okay, so we can singly oxidize, well, we're singly oxidizing both of these. So if we do a single oxidation, still gonna get a ketone here. For this second one, this will oxidize this to aldehyde. All right, SOCl2 is a reaction that we talked about Monday. So this will essentially do an SN2. You're going to replace OH with a chlorine, which means we're going to have to flip our stereocenter here. And we should get this. PBr3 does the same thing with bromine. So just kind of as a point, we are flipping this stereocenter here. So someone asked if you could flip this and put the double bond O up and the H down. Yeah, that's fine. This is a like freely rotatable bond, so it doesn't matter if this is up or down here. This is our only stereocenter that's getting flipped. We don't do anything to this center and this center here. So when we do this reaction with PBr3, we can kind of ignore the majority of it. This is the carbon scaffold that we're going to have. When we attack at this center, that's the only thing that's going to get inverted. And we're going to get this product. So a common mistake I see, is it the same as SOCl2? Yeah, it's essentially the same as SOCl2. You're just using bromine instead of chlorine to do your reaction. Okay. For Grignard reactions, aldehydes and ketones act the same. You can still only do a single addition to them. A lot of people think that you can do a double addition to these for some reason. That tends to be a common mistake I see. But really, the only time that ever happens is with an ester. So both of these are going to end up getting a single addition. And I might write this one out. So we have two different, we have excess Grignard solution, so I'm going to draw them twice. Both of these can attack our carbonyl center. Kick up our electrons. We'll get a bunch of O minuses. We're adding 2 carbons for both of these, so 1, 2, 1, 2 here. And then our last step, we add water. So we'll make the diol. Like so. This is going to be different from the next problem where we actually have an ester. We can actually do this twice. So that will change things a little bit. So taking a look at the ester. It's a 6-membered ring. Okay. Nope. Here. So this is a little different. You can do 1 Grignard with a ketone or an aldehyde, and you can do 2 of them here. Because once we do the attack, we can actually kick out this ethanol. So if I draw this one, and I do a 3-carbon, yeah. I'll draw 2 MGBRs for this first part. One of them can attack at our ketone. The other one can attack at our ester here. This is going to three carbons. 1, 2, 3. 1, 2, 3. Give us something more complicated. So now this one here is essentially done. It only has carbon-carbon bonds attached to it. There's nothing you can kick out. This one, on the other hand, has a carbon-oxygen bond, which is pretty weak. So these electrons can come down, kick out ethanol. We've still got an O minus. We've lost this ethanol here. We've reformed a ketone. Someone had a question in the chat. Oh, sorry, Kyle's back. Okay. From here, our Grignard can come in and attack again.
They all just went away.
At this point, we have O minuses that are all bonded to carbons, nothing to be kicked out. When we add in our water, we can get to our final product. Which would be this. So when you see these kind of questions on your guys' exam, it's important to identify like ketone, it'll do a single Grignard, aldehyde will do a single Grignard. This one will do a double. This one will do a single here. Someone asked if I can go back real quick. Put them both on the same page. And then you're kind of going from there. So looking at this, I would add one equivalent to this one. I'd add two equivalents here. Same thing with like, if we did the exact same question with sodium borohydride, or sorry, LAH. The H is in red. Oh, it's a crappy looking OH. When we do this with a Grignard, we're doing the exact same concept. We're going to get OH, OH. We're just adding three equivalents. 1, 2, 3, 1, 2, 3, 1, 2, 3. Yeah. So someone has a question in the chat. In the second Grignard reaction, why did the second oxygen go away after we moved the other oxygen pair down? Oh, so why did like the alcohol go away? You could also technically say that this is a product for your reaction. Generally, we don't really care about these little alcohols that get kicked off. If you were to just draw this as your product in the exam, that's fine. We're not really looking for, it's very rare that like this is the reagent that you're trying to make from one of these reactions. Why did you add 2 to the one on the right side? So you add 2 to the one on the right side because it's an ester. Esters can be attacked twice. It's basically going back to this mechanism here where you can kick out this alcohol here. So when you kick it out, you remake another ketone and you're able to basically do the exact same reaction again. Versus over here, there's nothing to kick out. Carbon oxygen bonds are pretty weak. Carbon hydrogen, carbon carbon bonds are really strong. So these are kind of stuck where they are. They can't do anything. They can only do the reaction once. Okay, I'm going to talk through some synthesis problems. I'm going to give you guys a few of them that we may get to. We may have to do them on Monday. We will see. So the first one I'm going to talk through is this here. So one of the things that we learned in this chapter was how to make carbon-carbon bonds with aldehydes, ketones, esters. We can do Grignard reactions to make carbon-carbon bonds. Before this, we only knew how to make them through a terminal alkyne, some base, and some sort of haloalkane. But for something like this, it's going to be a real pain to try to turn this into an alkyne, do this reaction, turn it back into a ketone, something like that. So it's a lot easier for us to use this Grignard reaction. So what do we need? We need a aldehyde or ketone or an ester. If we look at the synthesis problem here, 1, 2, 3, and a bond to an oxygen. 1, 2, 3, bond to an oxygen. This is probably going to be our starting material here. I need to add 1, 2, 3, 4 carbons. If I'm doing a Grignard, I need it to be either an aldehyde or a ketone. We don't know how to make esters yet. So if I take this and I throw in PCC, I can get to here. And this really sets me up nicely to make this. So I need a Grignard 1, 2, 3, 4 carbons on it. One, 2, 3, 4 MGBr in water. That gives us the basic structure. When this attack happens, we end up reducing this down to an alcohol. So from here, we just need to do another reduction. We could throw in PCC again. Technically it's secondary, so we could also throw in chromic acid. And that could get us to our final product. This is something you're probably going to see a lot on these. You're going to have to do some sort of reduction or oxidation, and then a Grignard reaction. I want to talk about protecting groups a little bit more, though, because I think that's something. Oh, it's someone asked if PCC represents. I think that's 7 bonds. That should be 6. It's a strong oxidizing reagent, CrO3Cl, or sorry, it's a weak oxidizing reagent. You don't really need to know this structure here, though. Generally, we just write PCC. I'm not going to ask you to write that one out. Okay, so protecting groups. This is going to be another time when you're probably going to need them. So this is a really simple looking synthesis problem. It looks like it could be done one step. The problem is that if I threw a Grignard in with this, so we need to add 4 carbons. Is that Grignards really like deprotonating alcohols. This is going to give us this here. It's just going to pull off this OH. We have a reactive center and we need to quench it. So the protecting group that we talked about last time was TMS chloride. We're just going to keep using it. It should be MGBr. Sorry, it's always MGBr. That G probably did not help. So in order to be able to do this reaction, we need to protect this center here, or sorry, this center here. So if we throw in TMS chloride, and I believe pyridine, we are going to be able to make an O TMS group here from this point this alcohol is essentially out of the equation. So we can throw in 1, 2, 3, 4 carbon Grignard. We can make what almost looks like our final product. And then from here, we just need to remove this TMS group so we can throw in TBAF. And get to our final product. Okay, so this is a pretty simple one. I'm going to do a much more complicated one of these. That involves a lot of steps. It's probably a little more complicated than what you would see on an exam, but I feel like it's better to give you a more complicated one than give it to you on your exam. So okay, so looking at this, we can't just add in a Grignard. If we were to add in a Grignard, it would deprotonate our alcohol. So we're gonna need some sort of protecting group. We also can't just oxidize because I wouldn't worry about the mechanism for installing a protecting group. It's just an SN2. It's not really one I'm gonna test over. If we oxidize this to, so I'll actually draw this step out. Another reason why we're gonna need one. So say we just threw in PCC. Now we have a different problem that if we throw in the Grignard to make this side, it's going to attack here and here. If we throw in the Grignard, the methyl Grignard here, it's going to attack here and here. So I can draw those two out. Versus BH3 MGBR. They're both going to attack at both centers. So you're going to be kind of screwed when you're trying to make this compound where you have two different Grignards that are happening. So in order to do something like this, I'm just going to completely draw this. We're going to have to use a protecting group. We're actually going to have to use it twice for this one. So first time we're going to have to use it is immediately. So if we throw it in there, we throw in TMS chloride. We can now do our Grignard. So this is basically unresponsive at this point. Oops, that should not be, this should be an OH and a methyl. So we can throw in our Grignard here. We want to add another methyl group to this side, so methyl MgBr. Would get us to here. From this point, we are going to want to remove this protecting group because there's not really much we can do with it on there. If I want to do a Grignard at this center, I need this to be oxidized. This is tertiary, which means if I throw in an oxidizing reagent, nothing will happen. There's no hydrogens on there. So if I throw in PCC, I can get to here. So now I'm at an interesting position. I am essentially at the exact same position I was up here, where if I throw in a Grignard, it'll deprotonate this alcohol. So I have to use my protecting group again. TMS, Cl. I can throw in the Grignard for the other side, which is 3 carbons. Make what almost looks exactly like the final product. And then from here, take this TMS off. With our TBAF. So this is a more complicated version of these. Essentially, when you end up with an alcohol and you need to do a Grignard, what's TBAF? Kyle, you want to answer that one? It's essentially F minus plus a counter ion, which is some large, I think it's an amine. Okay, so I'm going to give you guys a few of these. We might get through one of them. And then we'll do the rest of them on Monday. What do I have for this?
What the fuck? Oh, shit.
All right, I'm going to give you guys a few minutes. Oh, I can get everybody. I'm going to put a stipulation in this first one, which is this has to be your only carbon source. which means we're gonna have to make two different reagents. There's kind of a hint that like this is one of these. This is the other one. So like if you're adding two of them together, you have to make something from this and then make something different from it. So we'll go over that in a minute. This needs protecting groups. So I'm gonna give you guys, maybe like 3 or 4 minutes to attempt this one. We'll go through it together. And I might even give you a hint as to what the two halves you're gonna have to make are. Wow, there's 8 messages. So my hint's that you're gonna have to get to these two different molecules and then put them together. They both have to come from this guy. All right, I've got a minute and a half. So the first side is kind of easy. If I want to make my Grignard reagent here, I can just throw in magnesium. This will get me to here. I can make this Grignard reagent. It needs to come together with a ketone in order to make this here. It'd be this plus this. And then the second step would be water. So making this guy is going to be a little bit harder. We're going to have to use some reactions from other chapters and then eventually oxidize it. So there's a few different ways to do this. I'm going to throw in a small base first. So NaH is a really small base. I can make an alkene if I do my anti-Markovnikov addition, so BH3 and THF, followed by NaOH and peroxide. I can make this alcohol here. Now I just need to oxidize it. Putting in PCC gets me to my aldehyde. You can't do an SN2 for this. Well, you can't do an SN2 in general because it's going to be a secondary center. If you threw in NaOH, it'll eliminate. If you throw in H or just water, it'll end up doing a rearrangement. This one's kind of a mess. But this gives you the two halves that you need. You can put these two together and get to your final product here. I am going to do the other two on Monday, so Friday. On Monday, so work on them over the weekend, and then we will go through them together.